Hey everybody, it's Mrs. C. I am here to go over scientific notation with you guys. By 8th grade, it's pretty normal scientific notation. I call it SciNot. It's pretty normal for you to have been exposed to scientific notation, but we're seeing that you're just a little bit woozy in the area of scientific notation, or what I call SciNot. And I just wanted to give you a quick overview so you could get some practice in your group. So really a very, very simple concept scientific notation is. So let's just go over the basics. Scientific notation is used to express very big numbers, or possibly, that's supposed to be a 5, extremely small numbers. I don't know, I'm just making it up as I go along here. All right, there's a really big number on the top and a really small number on the bottom. So the question in scientific notation is really, how do you express these properly without losing value, but maybe shrink them down a little bit so there's not so much going on? You know, the community of mathematicians, probably not, I'm just saying it, don't like all these commas, because these commas could be very easily, and I often do, confuse them with decimals or other algebraic or arithmetic notations. And so, you know, it's a little dangerous to have all this extra stuff all over. So enter the concept or the skill of expressing words and numbers, in scientific notation, or the reverse, taking something that's in scientific notation and actually understanding what its value is. So I'm going to try and break it down for you so that it's pretty clear. And let me start with the big number. So now I've got a big number, and I want you to target your eyes for a moment, please, on the actual numbers, not the zeros, the numbers. So there it is. So if when you're doing scientific notation, you can target the numbers and exclude all the zeros that are either in the front or the back, and I don't mean zeros that would be in the middle, or if I squeeze a 0 in there, I don't mean that. I mean numbers all in the back, or possibly if we're doing a decimal in the front. So the deal with scientific, I'm trying to erase what wasn't there. Okay, there we go. So the deal with writing a number in scientific notation is it has to look like it's in a particular form, and I'm going to explain what that form is. It's the number that I just boxed that you see above there, but it has to be a number, a decimal, and then, I'm sorry about that again, it's trying to lasso, and when I do a dot, okay, it's got to be the number, but there can only be a number in the tenths place. I don't mean to get all, technical with you using proper place value. There can only be one number in front of the decimal, and then it's got to be a bunch of numbers in the back. Now, the explanation of that is a whole lot more complicated than actually doing it. So let's just pretend for a moment you understood what I just said, and let me go on and give you maybe another color coding. Then it's always followed with times 10 raised to the, and there's the next question, exponent here. So this is the format you're always going to write a number in scientific notation in. You'll put a number that's here, that I just did in the orange, that will go in this box. And then the exponent, I'll talk about in 1 second. I'm going to leave it to the end because it's the easiest, I think. So we slide this number right there. And you see how this 5, went into the number in front of the decimal position, and then the 2 and the 3 just filled in the back. And that's what you always do. You just take whatever number you boxed, slip it into the format that has a number point something, and however many somethings are in the back, you just fill them in the back. Now, this is an example, this is a lesson on how to do scientific notation, not how to understand what you're doing. I just want you to get into the habit of doing it, and then what we'll do is we'll go back and we'll take a look at it and try to understand why all of this works. But right now, if you could just get into the habit of doing it, I'd be happy before I try to explain it. Now, I told you this green over here, if you see it, it's still a box of green, is the exponent that goes in this proper format. And the exponent is a two-part exponent. You have to tell me whether it's positive or negative, and then you have to give me a number. And so, first thing I want you to do to decide if when you put something in scientific notation, to decide whether it's going to be a positive or a negative, it's as simple as looking at the original problem and asking me, is that a big number or a small number, whole number versus decimal? The decimal numbers are the ones that get the negatives. And the whole numbers, this big, huge, what is this? Hundreds, we got thousands, we got millions. This is a 5 billion number. Big number. 5 billion. And therefore, it's going to be a plus. Had it been 0.0000523, that would be a decimal number in my mind, and it would have gotten the negative. So first of all, I know it's a positive. All I need to do now to be done with this entire thing is go to the first number. Now, if you notice, the first number that I'm talking about, it was the one that we put the decimal after, right? And that's this one. All you need to do is tell me how many numbers are behind this line to the right. How many numbers are behind the decimal? Now, I like to do the little whoop-de-whoop. 1, 2, 3. I have no idea why I like to do this. 4, 5, 6. It just seems more fun. 7, 8, 9. There are 9 decimal place values behind the decimal that I put when I was writing in scientific notation, and that is the number that goes here. I told you it was a positive, so I don't have to write it. So the way we would express this number in scientific notation without all of the dialogue. What did I say? 5,230,000,000. It was 5,230,000,000. Okay, this is the number I gave you. So to just recap, we wrote 5.23 times 10 to the positive, and it was a 9. And what that means is we had the 5.23, right? And we agreed it was 1, we agreed it was 1, 2, 3, 4, 5, 6, 7, 8, 9 place values after that first spot, see, the decimal. So I fill with zeros, and I've actually rewound the problem, right? I actually have the original. See it? This one and this one match, and that's the whole point of scientific notation, is the values are the same. But do not be confused here. The answer is not what I just did. This is the check step. That was me making sure I did it right and showing you that it's the same value. That wasn't the answer. We were asked to write a number in scientific notation, and we did it. So the way you express 5,230,000,000 in scientific notation is simply 5.23 times 10 to the 9. And I do allow, and in fact encourage you to use the X when doing scientific notation, because that's the way they do it. That's the way they show it in the textbooks. So that's the way I will accept my scientific notation. Now, I know for a fact that you guys were taught how to do this. I'm not sure if it didn't sink in because you didn't have enough practice on it, or because you didn't understand it, or I don't know, maybe something strange did happen that kept you from learning this huge mathematical skill that everybody learns somewhere in the 6th and 7th grade. I don't know what happened, but surely it's an easy one to backfill. It's really no problem. So I'm going to show you another one, but I'm going to change it up a little bit. I'm going to give you a decimal. So I have 0.001 0, 4. Okay, so now place value, tens, hundreds, thousands, 10,000s, 100,000. So the name of this number is 104 100,000s. You're noticing I don't put the 0 in the front. I just find that it's not necessary. It's an extra 0 that's confusing. I would honestly recommend you stop putting the 0 in the front of the decimals too, because it gets in the way when we start counting how many moves that we're making. So do you remember the proper protocol to follow? It actually works the same for decimals and big numbers. Box the number you see. Now in this case, because we have a decimal, then the zeros, the extra zeros that are usually in numbers for scientific notation, are in front of your decimal, meaning these guys. On big numbers or whole numbers, the zeros are in the back. It doesn't matter where they are, you just need to identify who they are and how many there are of them. But do not be distracted or thrown off by a 0 in between two numbers. Zeros in between numbers are very important. They're holding a place value just like everybody else, but they count as the box number. So I wouldn't want to just box the 1 and the 4. How would I work around the 0 that's in the middle? I couldn't do that. You have to box the whole thing, which makes a lot of sense, honestly, if you think about it. So if you remember our format, we had the box, very simple. I said the times the 10. These ones in black are always there. They do not change. They never change to times 20 or divided by 10. And then there's going to be the question of the exponent. And I put that in green before. And the other thing I want to do here is just get going and fill in what I'm supposed to do. Now, you can try it if you think you've got the hang of it, but we haven't done a practice on a decimal, so just maybe listen to this real quick. I said you're supposed to put the 104 here, but you remember I said there had to be a decimal right there. So I said the first number and a decimal, and then backfill whoever else is there. So that's how you do it. A decimal must go after the first number. It's part of scientific notation's proper format. The next thing I told you to do was count how many moves either to the left or to the right it took you to go from that decimal place in the original number, if the original number had it, which it would have been here, right? How many decimal moves to get to the end? Well, in this case, it's 1, 2, 3. See that? I'm going left instead of right. That's all. So it took me 3 moves, but before I write that 3, I want to look at the original number, 0.00104. To decide if it's positive, I need to know whether it was a whole number or a decimal when I started. It's a decimal, and it's the one that gets the negative. And we said 3 moves, it gets the -3. So that would be how you would write it. So this would be written in scientific notation, 1.04 times 10 to the -3. And you see I rewrite it without all the boxes. That's the proper format. Okay, I think we just need to practice a little bit. Let's come over here and let me give you a little bit of practice. There we go. All right, guys, this is coming off of the CUDA software worksheet program that's on the internet. I don't know why it's not moving for me. I really don't care. I'm just going to do it like that. Okay, so one more time. This is coming from CUDAsoftware.com. It's free worksheets, but it's free worksheets pre-algebra. So when you go to look for extra practice with answers, you've got to go to the pre-algebra section, and it's under, I believe, exponents, scientific notation, and then you're going to see it, and there's more where this came from with answer keys. So first thing I want you guys to do is just take a look at these problems, and let's see if we can box the answer. Just on 1 through 6, let's just box the answers. Now, I'm going to make it a little bit bigger, easier to box. So for number 1, we'd box that one, right? For number 2, what would we box? Well, we just box the whole thing. There are no zeros. That's weird. And then on the other one, box that one. You see how I just went and I boxed the number excluding zeros? Can I just ask a question? I don't know if anybody's asking the same. Why would we want to write this in scientific notation? If scientific notation was written, or was it invented, to express very large or extremely small numbers that take up a lot of space, so that we could condense them and write them smaller, why in heaven's name would I even want to practice on 4.7? I really wouldn't. They give those to you to confuse you, to throw you off, to see if you know how to actually show a different value expressed in a different way. You would never write number 3 or number 5 in scientific notation. Number 1 is different. Again, number 2, why would I want to write that? In scientific notation is going to make that number longer. Now, how do I write it? How do I box it? You box the number, ignore the 0. On the next one, box the number, ignore the zeros. On the last one, box the number, ignore the zeros that aren't there. Okay, and so it goes. I just want to throw another one out because I was just thinking about it. I didn't know if you were or not, but I'm just thinking of a number that looks like this. What about 304? Another number you wouldn't want to write in scientific notation, but if I told you to box the number, ignore the zeros, sorry, the whole number is going to have to be boxed because the 0 that's in the number is in the middle. Remember I said you can't ignore numbers that are in the middle. All right, so we boxed all the numbers. Easy. I just want to go over and ask you, do you know whether they will, when you write them in scientific notation, will they be an exponent that's negative or an exponent that's positive? So let's take a look at number 1. Will number 1, that's this one, will number 1 get a times 10 to the negative or times 10 to the positive? It's going to be a negative because it's a decimal number. What about number 3? I'm going to go down. Number 3, positive. What about number 5? Negative. What about number 2 over on the right? Positive. What about number 4? Positive. What about number 6? Positive. There were only 2 decimal numbers, number 1 and number 5. The rest are positive exponents, not positive numbers. I hope you're listening and you don't have me on mute. These are not negatives because they're negative numbers. They're not. They're positive numbers. The decimal is negative, which indicates the direction that the decimal moves. And again, that's about understanding. You don't need to understand it, except to know these are all positive numbers. It's the exponent that's negative or positive. So please just don't get confused with that in the future when I go over it. All right, now I want to do a couple examples. Like I said I was going to. I don't want this video to be 1,000 minutes long. Doesn't seem like I've been talking for 20 minutes. Let's do number 1. Now, the first thing I told you in number 1 was to write the boxed number with the decimal after the first. 7.86. There it is. Now, it's going to be times 10 raised to the, is it positive or negative? That's right, we just said it's a decimal, so it's negative. The last thing for you to do is count how many moves from the number 7, from the behind the 7, to the decimal. So you count. It's very hard to do the little whoops, I'll tell you that. Here, I'm going to try. 1, 2, 3, 4, 5, 6, 7. It's 7 moves from the decimal. That means from where you put it here in the orange. 7 moves, and remember, I already put the negative, so I couldn't forget it, times 10 to the negative 7. And that is the final answer for the scientific notation of number 1. Now I'm going to do the scientific notation of number 4 because it's the one that makes the most sense to me to even write in scientific notation. Did that one. Okay. Number 4, I boxed what? 126. So I write 126, but with a decimal after the 1. I write, if you don't mind me keeping it, no, I want to keep it the same. times 10, that's the one that's always there, raised to the, did we say it was positive or negative? We said positive because it's a whole number. And how many moves from the decimal place behind the 1 to the back? Well, it would be 1, 2, 3, 4, 5, 6, I hope. And so the final answer is 1.26 times 10 to the 6th. Easy breezy. Now, when you do a number like number 3, number 3 is so simple and easy that it confuses a whole lot of people. First of all, we boxed the number 4.7. So we write 4.7. You notice we haven't had a decimal. I just say thank you very much for giving me the decimal, because now I don't have to put a decimal behind the first number. There's already a decimal behind the first number. So that actually eliminated me doing anything. So my box number that I put here is in its proper form, decimal and everything. I didn't even have to do anything. So I write my times 10. I ask myself, and here's the tiny little bit of a glitch in my, well, not a glitch because this is how I told you, but I don't want you to get confused. I tell you to look to decide if it's a decimal number or a whole number, and this one's a little bit of both. It's got a 4 and it's got a 0.7, so it's a combo. It's a mixed number in essence, right? Well, here's the deal. Is it a small number, meaning a number less than 1, or a big number, meaning a number bigger than 1? And I didn't want to get into that with you initially because I didn't want to confuse you. But this number, 4.7, is a number bigger than 1, so it qualifies as that whole number, or the big number, not a tiny number like number 1, which is a decimal number less than 1, meaning there is a 0 in this position. All right, so being that 4.7 is a number bigger than 1, it would be a positive move, and that means it would be a plus. Where'd my green go? I'm in green. Now, here's the fun part. How many moves do you have to make? Well, you don't want to make any moves, because the movement would change the value from what we're making it, 4.7, and it would make it, say, for example, if I put a 2 here, it would move it 2 places there. If I put a -2, it would move it 2 places there. I don't want the decimal to move at all, because already it's in the form that it would have to be, which is why I said this was a stupid problem to begin with. Because you don't want it to move. Therefore, in scientific notation, if I was forced to do it, I would say times 10 to the 0, meaning don't move the decimal anywhere. Now, in mathematics, 10 to the 0 has a value of 1. If you use your calculator, you'll verify that very strange fact. If you do 10 raised to the 0, enter, it's going to tell you 1. And don't we know that 4.7 is actually equal to 1? Yes, we do. All right, so number 3 was a trick. And I'm going to erase it because we do have to attend to the tricks. Let me do one that's a little bit close to a trick, but not completely. Number 6. Now, number 6 is 1.75, right? Because the box number is 175, and we have to put the decimal there. Now, to go from 175 to 1.75, you see how we do want the decimal to move because they're not equivalent. How many places do you need the decimal to move so that it matches 175? It would have to move 2 places, 1, 2. And that is how we decide what the exponent is going to be. So it was 1.75 times 10. 175 is a big number. It's a number bigger than 1. And so 2 moves, positive 2. Whew. And that, my dear children, is that. That is how you express a number in scientific notation. Now, I know the video is getting long. Unfortunately, there's a lot of information to go over if you don't have the recall from before. I am going to switch my color and come up here for a minute and just focus on these. This we've already done, so there's nothing new. We're just going to reverse the process. That's all. Okay, so in reversing the process, we're writing the number in standard form. We're taking what it gave us, 6.17, and we're moving the decimal. If it's a positive, we're moving it to make the number bigger. If it's a negative, we're moving it to make the number smaller. I find that's easier than telling you moving left or right. I honestly do. Because if you're going to make the number 6.17 bigger, which direction are you going to move the decimal? To the right. Everybody understands that. So 1, 2, 3 places. Isn't it true that 6,170 is bigger than the original 6.17? Yes. And if the exponent is a positive, then that is what you're going to do. You're going to make the number bigger. And guys, we just did the answer to number 7. That is the answer, 6,170. A lot easier the second time around, isn't it? All right, look down at number 11. The number they gave us, 6.7. And they're asking us to move the decimal -3. So -3 is going to make the exponent, -3 is going to make that number bigger or smaller. It's surely negative is going to make the number smaller. Which direction do you need to move the decimal to make the number smaller? You move it to the left, because if you move it to the right, 1, 2, 3, you're going to have 6,700. It's supposed to be getting smaller. So we got to go 1, 2, 3 and fill in the zeros. Not 3 zeros. No. It only wound up being 2 zeros because it had to whoop around the 6. So this final answer is 0.0067. And you should always do a little quick check step. If you had a negative exponent, your number should be smaller, and in decimal form smaller. If you had a positive exponent, your number should be bigger. Now, I want you to take a look at the one in the middle that I left out. I'm just going to get rid of all this extra stuff. The one in the middle, should it be getting bigger or smaller? Should be getting bigger. It's a positive 6. So 7.31, 1, 2, 3, 4, 5, 6. Fill in with zeros, commas, please. 7,310,000. And do not box that. You need to box your answer nice and clean with no whoop-de-woos. Okay, that's how you do it. Now let's come over here and take a look at these. All right, we've got one decimal number, one that's going to be a tiny number, one the other two are going to be the big numbers, and you probably see them. Number 8 would be 7. There is no decimal because it's implied that it's after the 7. They didn't have to write it. 4 moves. To make the number bigger, you're going to go to the right. 1, 2, 3, 4. Fill in with zeros. The answer is 70,000. Now, if you want to be lazy, I guess you could... Oh, that didn't work. I was going to say, if you want to be lazy, you just erase. But that didn't work for me. Here's a decimal number. So 5.4, making it smaller. 1, 2, 3, 4, 5, 6, 7, 8. Wow, talk about your tiny numbers, right? I'm not going to rewrite that one. You're just going to have to go with me on that one. And that would be the final answer. Okay, fine, I'm going to rewrite it. I can't help it. I can't help myself. So it's going to be a decimal point and 1, 2, 3, 4, 5, 6, 7 zeros. Be careful to always make sure you have the appropriate number of zeros. Last but not least, number 12, moving 2 places to the right to make the number bigger. 1, 2, like that. And then the final answer would be 959. All right, my babies. That was 30 minutes of a review of how to do scientific notation, which Mrs. Naparlo said pretty much everybody across the board was confused on. So now you have enough information to work in your groups, practice scientific notation, make sure you're checking your answers every single time until you get the hang of it, because you don't want to go and agree on a wrong answer. For those of you that think this is easy, believe me, this year in Algebra 1, scientific notation will come back with a little bit of a saucy edge. And so you don't want to judge too quickly. Make sure you know what you're doing here because, in a few months, maybe about 3 or 4 months, I'm going to add something to this that's going to change the game quite a bit, make it the same concept, nothing different, but I'm going to add some layers on top of this. So I need you to know scientific notation, guys. And there's no forgetting it, please. No more when we get to it in 3 months, you got to watch another 30-minute video to remember how to do it, even though the video will be here for you. So one more time, this is writing scientific notation and also writing numbers in from standard form into scientific and from scientific into standard form. Now what you got to do is get out there and practice. See you guys on the flip side.